This conference will now be recorded.
Very good morning, students. We have been discussing the previous year's questions from the JEE Mains papers. So today we are going to discuss numerical problems from the JEE Main papers 2021 31st August SIP 2 paper. And here I have collected some questions from the 11th part for today's discussion. So let us start our discussions. This question says a system consists of two identical spheres, each of mass 1.5 kg and radius 50 centimeter at the end of light rod. So you can see the system over here I have drawn for your understanding. So there are two spheres, each of them are identical in mass and radius. Okay, their radii also the same. Radii actually 0.5 meter, I can say 50 centimeter means, and mass is actually 1.5 kg. Okay, now the distance between the centers of the two spheres, that is given. Okay, this distance is given. So this is 5 meter. What will be the moment of inertia of the system about an axis perpendicular to the rod passing through its midpoint? Look, this midpoint, through this midpoint, if I pass an axis, so suppose this is the axis with respect to which this may rotate. Okay, this whole system may rotate. Okay, so what will be the moment of inertia about that particular axis? So this axis is actually perpendicular to the rod. Okay, and passing through the midpoint, and see this midpoint I'll take. Suppose this is the center. So from center, it is half of the center to center distance I am taking. Okay, so this will be 5/2 meter. Okay, now what will be the moment of inertia of this system? So this is actually very simple and straightforward question. So how do you do that? Actually, you have to find out the moment of inertia of each sphere with respect to this axis, which is a parallel axis to the diameter of the spheres. Okay, so if I consider a single sphere, okay, suppose this one, so I know the moment of inertia about its diameter. Okay, and this is this axis, this is parallel axis at 5/2 meter distance away. Okay, so then moment of inertia will be, see, this will be same since this is identical, so I'll just do the same thing. Okay, I'll apply the parallel axis theorem for both, and since both the spheres are having same mass and radii, so I can just multiply 2 into, see, moment of inertia about diameter 2/5 m r square plus m into 5/2 square. Okay, so this will be the moment of inertia. Now matter of calculation. So let us go to the other page and do the calculation. So what is m? I know. So let me write I is equal to 2 into m. M is 1.5 kg 2 by 5, 2 by 5 m r square. R square is actually 0.5 square plus 1.5 m r square. R square is actually 5 by 2 square. Okay, now let us further simplify the calculation. So this is, let us say, 15 into 2, and this is 25 into 10 to the minus 2. So I'll just multiply 10 to the minus 1 here. So 10 to the minus 3 plus this one will be 50 into 25 divided by 40. Okay, this 1.5 I have kept there. Look then what I get. So this 2 I will multiply inside. So it will be 15 into, so this 2, so 4 into 25 will be 100. So this will be 10 to the power minus 1 plus, here it will be 15 into 25 divided by 20. Okay, so what I can do, I can just take 15 common from both. Okay, so I have 1 over 10. Here I have, see if I simplify this, 5 5s are 25, 5 4s are 20, so 5 by 4. Okay, let us do this. So this will be actually, see, it will be 20. Okay, so 2 5 2, so 20, 2 plus 25. So what we get? We get 15, 27 divided by 20, right? This I can do like this, 5 4s are 20. So I have 81 divided by 4. Just let me check. Okay, so here it is all right. So 1 over 10, this is fine. 27, this is, yeah, all right. Let me, so it will be 81 divided by 4. Okay, it is giving some overshoot values. Let me check once again whether I have done some mistake over here. So this is 0.5, this is r square, 25 by 4, fine. This is again m, 2 multiplied. Let me check whether I have multiplied 2 over here. Yes, I have done that. So there should be, I think I have 1.5, fine. 10 to the power minus 2 from here. 1, this is also fine. I see. So this is actually the mistake I have done here. So this will be here 75. I'm sorry. So this is 75. 75 into 5 will give you 375 over here. Okay, so I think I had done a mistake over here. Look, okay, I see. Just a minute. Let me cross check once again. Two by 5 mr square. Okay, 2 by 5 mr square. Fine. So 2 by 5 mr square. This is mr square plus mr square. Mx square. Okay, this is x mx square. Okay, just let me repeat the calculation. So I hope you are expert in calculation. I always do some small mistake in between. Let me just repeat it. Okay, so we have, let this gap 2 be here. So I have 5 by 10 here. I have 2 by 5, so 25 by 100 plus 25 by 4 over here. Okay, let us do in this way. So this is 3, 5, 2, 2 goes off. Okay, so this 5 I can make 20. Okay, so 3 by 20 here, and here I can write 5 3s. This is 2. Okay, so I have got 75 by 8 over here. Let me just go with this. Let me multiply. This is 3 by 10 plus this is 74 by, sorry, 75 by 4. So this will give you actually, so this will be, so 10 4, so you'll get 5 5, so you have 20 in fact. Okay, so 20, so this is 6 plus 5, this. Okay, so let us see what we have. Yeah, so we have 381 by 20. Okay, so I think this is fine. Yes, so this will give you 19.05. I don't know. Okay, so this is actually giving me 19.05 kg meter square. So dear students, you should not do the silly mistakes in between in the calculations. Don't be so casual as I was doing initially. So the first option will be the correct answer for this question. This is very simple question, just a matter of calculation. So let us go to the next problem. So this problem is also very simple. Let us read the problem. The problem says RE with the radius of the earth, then the ratio between the acceleration due to gravity at depth smaller below and height r above the earth's surface. So what we have to get, so suppose this is the earth, this is having radius re, so g at a height from the earth's surface I have to find out, like I have to write down the expression for that, and at any depth from the, suppose this is the depth smaller, so here at this particular position I have to find out g. Okay, and then take the ratio. So let us say this is g height h and this is gd depth. I have to get the ratio of these two. This is very simple if you read this particular condition. What is this condition? This r, the depth or height, is much less than re. That means we can actually write down the formula with approximation. So g d, we know depth will be g into 1 minus small r by re. A is by r, right? Sorry, d by r. Anyway, so that is re. So since I am able to apply this, I can write this also as 1 minus 2 small r by re. 2a is by r and 2 sorry, d by r. So that is what I had to do. I'm sorry, this will be actually formula was, let me just write in terms of class itself here. So in case of depth, it will be multiplied, right? Okay, let me just do this. Height, actually let us write it here. GH will be actually G by 1 plus small r by this whole square, right? So this is the thing I have to write actually. Sorry. G by 1 plus r by re whole square. Okay, if we write this, this g will cancel each other. 1 minus re by r into 1 plus r by re. See, what I was writing earlier was not wrong, but with respect to the question given, you have to write the formula. Okay, so now this is whole square. See, it is just multiplication job, and this is a plus b whole square, 1 plus r square by re square plus 2r by re. Okay, 2ab, right? So this is the thing. Now if you multiply and simplify, what you get, 1 plus 1 plus r by r minus r square by r e square minus r cube by this r cube. Okay, so this will be actually your answer. So where is that option? See this option. This is plus and both of them are negative. Okay, so this C, option C will be the correct answer for this question. Okay, so this was, see, this was, not very tricky, but by seeing the options, you have to actually understand how to write GH and how to write G depth. Okay, all right. So let us go to the next problem. This question says consider two separate ideal gases of electron and proton. So I have ideal gas in a container, ideal gas of electron and ideal gas of proton. Same number of particles. Okay, same number of particles. The temperature of both gases are same. Okay, both of them are in same temperature. You have to find out the uncertainty, the ratio of the uncertainty in determining the position of an electron to that of a proton. That means, see, you might be knowing what is uncertainty. So uncertainty in position is del x, uncertainty in momentum is del px. Okay, this is uncertainty in position, uncertainty in position, and delta px is uncertainty actually I have written tt, uncertainty ty, uncertainty in momentum. See, according to Heisenberg, for a microscopic particle or quantum particle, position and momentum according to Heisenberg, for a quantum particle, position and momentum cannot be accurately measured simultaneously. Okay, cannot be measured simultaneously to the arbitrary precision. Okay, or arbitrary accuracy. So for that, there is a product called uncertainty product, and that is delta x into delta p, that is always greater or equals to h cross by 2, or h cross means h by 2 pi, so I can write h by 4 pi over here. Okay, h by 4 pi. So for the sake of calculation, we take this as equal sign, delta x delta px is equal to h by 4 pi. So this is the uncertainty product. So from here you have to see, here actually the temperatures are same for both the ideal gases over here. So ideal gas made of electrons and ideal gas composed of proton, they are actually having same temperature, and we know the RMS velocity V RMS is equal to square root of 3 RT for 1 mole, 3 RT by m. Okay, 3 RT by m. That means this R is constant, 3 is constant, and temperature of both of them are same. So I can say V, the RMS velocity is inversely proportional to the square root of their mass. Okay, in this particular problem. Now what I have got uncertainty product delta x delta px is equal to h by 4 pi. That is also a constant term. Okay, this is constant term. See, I have to find out the delta x, the uncertainty in the measurement of position. That is 4 pi into delta px. Okay, so I can write this as 4 pi m into delta vx velocity. Okay, can you write or not? Yeah, we can write. So look, this term is constant anyway. So what I have, see, if I write the expression for the velocity we had got for RMS velocity, so m, this was actually proportional. I have to find out the proportionality relation. I'm not writing 3RT and all. So this was actually having relation like this. Okay, so what I'll get h by 4 pi. This thing actually I can just strike off, not an issue. So this is actually proportional to 1 over root over m, right? So I can write delta x for electron divided by delta X for proton. Since I know this is inversely proportional to the 1 over, like inversely proportional to the square root of m. So this will go here mp. Okay, so I can write this as mp by me. Okay, we'll just check whether we have options over here. Yes, so you can see that we have got this option. We have actually got two options like this. Okay, mp and me. So you have to find out which one is actually correct. Actually the correct one is this one. Okay, so we have got that mp by m, square root of mp by m1. So uncertainty ratio of uncertainty in determining the position of an electron to the proton is this. Okay, square root of p by me. Okay, mp by me. So option number B was the correct answer for this question. Now actually see, you can analyze from here also. Since I have a delta x and delta px constant. Okay, so delta px constant, some constant term. So it depends on, see, it depends on delta px, right? So you have proton and electron, right? So in case of proton, you have greater mass, right? Greater mass. So you'll have lesser probability or lesser uncertainty in delta x. See here, these are in inverse relation. So for electron, we will have greater probability to, like, greater uncertainty, because this is much more tiny than the proton. Okay, so this is physical understanding. Okay, so it has, like, electron will have greater uncertainty than the proton in determining the position. Okay, so I have got a very simple problem here. If velocity v and time t and force F are chosen as the base quantities, the dimensions of mass will be what? So dimension of mass you have to find out. See, better to write down the dimension of all of them. So velocity, we know L to the power -1. Okay, dimension of time is just t. Okay, just t. Dimension of force we have to write down, that we know m L to the power -2. So I have to get dimension of mass. That means I will have dimension of mass means m L to the power 0 to the power 0. This I have to get. So out of these three, how do I get that? So look this, if I divide with this one, okay, what I will get? So let me divide this f by v. So dimension will be m L to the power -2, here L to the power -1. So it is giving actually m to the power -1. M to the power -1. Now if I multiply with this t, so what I will get? T plus here. So 1 2 will be multiplied here with the plus. So you will get the dimension of mass. Okay, so ft or tf v to the power. So I have dimension of mass from here. If I write f t v to the power -1. Okay, so look this, option B will be the correct answer for this question. Okay, all right, so this was really very simple problem. Now I have got another problem which is actually very simple if you can remember the formula. So let us see, this is from thermal physics, heat conduction. So two thin spherical metallic cells of radii R1 and R2, where R2 is greater than R1, are placed with their centers coinciding. Okay, let me just give you the figure over here. So just suppose here there are two metallic spherical cells. See this one, see, since R1 is less, so let me take this having radius R1, and the other cell, the outer cell, has radius R2. Okay, so these are actually two spherical cells and their centers are coinciding, and in that way they are kept. Now the question says a material of thermal conductivity K is filled in the space between them. So in this region there is a material having thermal conductivity K is inserted. The inner shell is maintained at temperature theta1. So inner shell is maintained with temperature theta1, and the outer shell is maintained temperature theta2. Okay, now rate at which heat flows radially through the material. Okay, so through the material there will be flow of heat if suppose, yeah, so you know what we have now. See, I have this thing, so there is in between some material which has thermal conductivity K, and now if these two are maintained with certain temperature difference, so there is a temperature gradient, right? So wherever there is a temperature gradient, there will be flow of heat, that is for sure. Okay, so then, so I have to find out what is the rate. Rate means, you know, dk, so dq by dt. We have to find out what is this rate, and if you know this formula for this, then it is very simple. If you don't know, let me tell you what you have to do. So before I solve, let me give you the options over here. Since options are lengthy to type, I have to write here. I have the photograph of that. Let me write from there. So the expression says, see, options are pi r1 r2 theta2 minus theta1 by r2 minus r1. This is one option. Option 2, option B, k theta2 minus theta1 r2 minus r1. Okay, and divided by 4 pi r1 minus r2, and this option C is k theta2 minus theta1 divided by r2 minus r1, and option D says it is 4 pi k r1 r2 divided by, sorry, theta2 minus theta1 divided by r2 minus r1. Okay, these are the options. Okay, so see, I know dq dt, this formula I am writing here. So it is directly proportional to k, directly proportional to the area if the area is constant, and then there will be temperature gradient theta 2 minus theta 1 divided by the distance, that is L. Okay, so this is in general the formula. If this A is constant, if A is constant, this is the formula. But in this case, you look, if I say the temperature flow is happening, heat flow is happening radially from out to in, like this, okay, in to out, then say the area is actually getting shrunken. Okay, area is not, area is actually getting sunken. Okay, so area is not constant. If I go from out to in, see the area is greater out and less inside, isn't it? So for this, what we have to do, instead of writing the whole area constant, we have to take an elemental area. Let me just do it. Let me clean this. Okay, so anyhow, I know this is theta 1 temperature, at theta 1 temperature. So look what I'm doing. I'm just taking an elementary cell at a distance small r and having thickness dr. Okay, having thickness dr. Okay, this thickness dr. Okay, so what I can write this area, see, let me write it here, dq by dt, which I have to find out. So see, for this particular uh, cell, okay, elementary cell, what I'm writing, this k is constant anyway throughout. Area will be 4 pi small r square, and temperature gradient, let me write for the time being d theta. Okay, temperature gradient here at theta, this is, temperature gradient, I can write d theta by dr. Dr is the thickness, right? Dr is the thickness. So this is actually the heat flow rate for this particular elementary cell. Okay, now what I have to do, I have to integrate. Okay, let me just write this dq by dt as q dot. Okay, so that expression I can write here, q dot is equal to k, I have 4 pi r square I have written, divided by dr, and here this is the d theta. Okay, now from here let me write dr this side by r square, and here 4 pi k divided by q dot into d theta. I have 4 pi k by q dot. Okay, dr by r square. Okay, now both sides let us do the integration. So integration, see, since the heat flow is happening from out to in, I'll write here r2 to r1, and here I'll write theta 2 to theta 1. Okay, because high temperature to low temperature, always heat flow will be happening. Okay, so if we integrate this, what I'll get minus 1 by r with the limit r to r1, and this side I'll get 4 pi k by q dot, and this is theta 1 minus theta 2. Okay, so obviously this is a negative quantity, Okay, let me then absorb this negative both side. So what I'll write the lower limit first, r2 minus 1 over r1. Okay, so I think this is okay. Let me just go with this, whatever we have. Okay, so I have r1 r2 over here like this. Okay, and see, I'll just absorb here the minus sign 4 pi k by this, writing theta 2 minus theta 1. Okay, so from here we'll just get our q dot, that is the question we have to find. See, this thing you can write actually r2 minus r1 divided by r1 r2. Okay, so look from here, q dot I can write, see, this is the 4 pi k by q dot theta 2 minus theta 1. Okay, so now q dot I have to write, so q dot along with q dot, this will be multiplied, so q dot will be roc 4 pi k 4 pi k 4 pi k r1 r2 divided by r2 minus r1 and theta 2 minus theta 1 as it is, theta 2 minus theta 1. Okay, so this is the answer. Let me see the options over here. See the last option, 4 pi k r1 r2 theta 2 minus theta 1 divided by r2 minus r1. So look, this is actually the formula itself is the answer. Formula itself is the answer. Only thing you need to find out, or you need to remember, that here it will be theta 2 minus theta 1 instead of theta 1 minus theta 2. Okay, so in general you might have read that temperature theta 1 is greater than theta 2, the heat flow is happening inside to outside, but in radially outward. But in this case, the question asked here is the heat is flowing from like flowing inward. So that is the point you have to remember, otherwise things were same. So this is just formula. So if you know the derivation of the formula, and if you remember this particular formula, then things are done. See, in case theta 1 is greater than theta 2, then what you have to do, and see, r2 is greater than r1, this fine, this factor is fine, only this factor you have to write. See, these factors are all right. See, 4 pi k r1 r2 divided by r2 minus r1, this factor is fine, only here you have to write theta 1 minus theta 2. Okay, in case actually, in fact, in that case, this limit will be theta, yes, so theta 1 to theta 2 in that case. Okay, theta 1 to theta 2, theta 1 to theta 2 limit. Okay, when you go from, and here actually you have to write this limit as r1 to r2, r1 to r2. So if you take the limit in this way, you'll get actually the same thing what I have written over here. Okay, all right, so this was a simple thing, but you have to remember the formula to get the answer very quickly. Okay, so now we have got another problem. Probably this is the last problem for this session. Okay, so let us see that. What is the problem? The problem says, for a body executing SHM, the potential energy is always equal to kinetic energy. Is that true? Okay, let us see. Average potential energy and kinetic energy over a given time interval is always equal. sum of the kinetic energy and potential energy at any point of time is constant. Average kinetic energy in one time period is equal to the average kinetic energy in one time period. Whether this is true. Okay, so these are four options given related to the kinetic energy and potential energy and the total energy of a body executing simple harmonic motion. Now you have to find out from these four options which is correct. Whether only one is only two is correct. What is two? Two is saying average potential energy and kinetic energy over a given time interval is always equal for any arbitrary time interval, whether the average kinetic energy and potential energy will be equal. So that you have to find out. Then the average, okay, so option say B says option 2, okay, this will be 3, I think. Okay, 2 and 3, option 2 and 3 will be correct. See, this is not correct, that we'll see. And some of the kinetic energy and potential energy will be always constant, so one is actually constant. See, this is always true. Let me just show you here. The expression for the potential energy for a body executing simple harmonic motion is given by half k x square. Okay, k I can write m omega square. Okay, let me write that, half m omega square x square. What is x? X is the displacement at any instant of time. Okay, at any instant of time, this is the displacement. Okay, all right. What is the expression for the kinetic energy? So k will be half m v square. What is velocity? Half m a omega. Okay, a omega. So v is actually a omega and then it is actually inside square root of 1 minus x square by a square minus x square. Okay, so this is the thing. Okay, this is the thing. Okay, so this is omega square. Okay, omega square, this one. Okay, all right. So if we write the kinetic energy will be half m omega square and a square minus x square. This is actually the expression for the kinetic energy for any arbitrary displacement x. Now let me write one thing here, or draw the, okay, so just add them. See, at any instant of time, if you add these two, that is total energy. How you get the total energy will be actually, see, this half m omega square x square and here half m omega square x square, they will cancel each other, so you'll get half m omega square a square. This, see, a is amplitude, that is the maximum displacement, that is a constant quantity. M is constant quantity. Omega angular frequency, that is also constant. So the total energy at any instant of time will be actually constant. Okay, sum of u and k will be constant. That option is actually correct. So sum of kinetic energy and potential energy at any point of time is constant. Okay, that is fine. Now I have to see the average kinetic energy in one time period is equal to average potential energy in one time period. Let us find out what is average kinetic energy and what is average potential energy in one time period. Okay, so let me, for that actually I have to write x is equal to a sine omega t. Let us say this is the displacement at any instant of time t. Okay, at any instant of time t. Very simplistic equation I have taken here. See, I have to then write what is the potential energy and average time average. See, I'm writing finding out average whole time period. So this is, you can write in this way, 0 to t, and half. So this is u means half m a square x square. And what is x over here? X is a square. See, x is a and sine omega t. Let us put that here. So if we put that x over here, what I am getting? A square sine square omega t, and this is dt. I have to write this way. Okay, this is the time average. Okay, in a full cycle or one time period. So look, this term is constant. There is no time dependence. Let me write this. So only thing I have here is this one, which I have to do the integration, sine square omega t into dt. So whenever you have square quantities, sine square or cos square, so this integration, this whole integration will give you upper limit by 2. Okay, so this upper limit by 2, this is anyway 1 over t is there. So upper limit by 2 means half m omega square s square, and upper limit is t by, so upper limit by 2, that is t by 2, and t is there, so t in the denominator, so t will cancel each other. So finally what you get, 1 over 4, like 1/4 m omega square and a square. So this quantity I am getting. So average of kinetic energy, let us, sorry, potential energy, let me write the average of kinetic energy for one time period. So I know this is the same way I have to write 0 to t and k here and dt. So k is 0 to t, k is half m omega square, this is a square minus x square into dt. So x square I'll write here, x I have taken a sine omega t, so you get here half, sorry, 1 over t, and see this term I'll just keep inside, sorry, outside, half m omega square, let me write it here, and I have 1 over t integration 0 to t, and see I have a square minus x square, I'm writing as a square sine square omega t into dt. See this term I can write half m omega square a square, let us take common, so 1 minus sine square will give you cos square omega t, right? This will be cos square omega t. So the integration is now 1 over t 0 to t cos square omega t into dt, right? This is my integration now. So as I said, so this also will give you the integration upper limit by, see, result of integration will be upper limit by 2. So half m omega square a square, this is common. Okay, so this is t by 2 here, and t I have here already, so I'll get half means here half, so this will be 1/4 m omega square x square, sorry, a square. So what I have got, see, kinetic energy, average kinetic energy in a full cycle, and average potential energy in a full cycle. See, 1/4 m omega square a square, and here also 1/4 m omega square a square. So both are same actually, right? So this is equal to average of potential energy in full cycle. Okay, so but it is actually not true, it is not true for any arbitrary time or at any displacement. This average will not be, so this option will not be correct actually. Average potential and kinetic energy over any given time interval is always equal, that is not true. Okay, that is not true. The sum of, so I have got sum of kinetic energy and potential energy constant, this is correct. Average kinetic energy in one time period is equal to the average potential energy in one time period. This is also correct. So option D will be actually correct answer for this question. So with this, I'll stop it here for today. In the next class, we will continue with this paper, 31st August, SIP 2, but I'll take collection of questions from 12th part. Okay. So thank you for your patience. Bye for today.